So this section, the intent is to cover the many different applications that you can use with your WaterCAD and WaterGEMS model. We're going to talk about system planning, some tips that you can use there, setting pressure zones, using master planning, skeletonizing models, fire flow analyses. We will spend more time on that. Water quality studies and modeling chlorine concentration. That might be something that you might be using your WaterCAD WaterGEMS model for. Operational studies to figure out how best to set up the switches or the on and off for tanks and pumps to have the best water quality or to save the most energy, and that could be energy management. So maybe that's where you're headed with your water quality or with your WaterCAD or WaterGEMS model. Or perhaps it's rehabilitation studies to determine if you replaced a line in a particular area and it improved the C factor or the C value, the friction, how much of a pressure benefit would that yield for you? And you can answer those questions just by simply creating a new physical alternative, change the C factor, and compare and contrast the pressure and flow differences that you see either visually or in a graph somewhere. One of the first things you probably need when you're setting up a model is a system profile somewhere. A lot of times you might see these on the wall at a treatment plant. They could be getting brown over time, age because they've been there, and tank water levels haven't changed that much, and pump elevations haven't changed that much. But generally at systems, you'll probably find a system profile somewhere that shows some of the critical information. What's the minimum water surface elevation, off water surface elevation, maximum water surface elevation for each tank, and the pumps and the pressure zones. So it's more of an isometric view of everything in your network. Now, you can refer to the system profile maybe as a starting point when you're setting up the model, but of course you'd want to go verify site conditions to make sure that tank water levels are really what they are supposed to be. Now, let's start thinking about how tanks behave and how pressure zones kind of form or evolve in a system. So let's pretend that we have a tank already out there in the real world, and you want to build a little small subdivision right here. It's a nice plateau. It's got a good view of the valley down below, and there's a river over here, and it's a really nice view. You can see the valley. You want to build a subdivision here, and right now you've got 65 psi because of the static pressure from the elevated storage tank. Okay, you look at another spot, another location, and you think, okay, well, what if we built a subdivision down here by the river? It's an even better view. In fact, you can even cast your line right into the water off the back of your house. Boy, wouldn't that be great to build a subdivision there or something. However, because of the static pressure, you've gone further down the hill, and now pressure is 130 psi. And as you heard, Dr. Walsky was talking about 125, 120 psi, and things start getting a little unfavorable for, say, your water heater or something. It just might not work out well. So you would need to create another pressure zone here and decide some place where you would put a PRV. And that PRV would then reduce the pressure downstream to where it's not feeling the full extent of that static head that the elevated storage tank would be delivering. Now then the pressure is something more substantially tolerable for the homes if you wanted to have a subdivision down here. Now let's think about going up the hill. We want an even better view at the top of the hill, and boy, we can see for miles around. However, pressure is 20 psi. That's not too satisfactory for us because it's so low. And we quite honestly would want a little bit more than the 20 psi. So how would we go about achieving that? What would we do next? All right, we would probably create another pressure zone, add a pump, and boost the pressure up to some satisfactory minimum average pressure. So this is how you can end up having multiple pressure zones in a small system. When you apply some philosophy like that to put in pressure zones, you need to think long term, because once they're in, it's very difficult to get pressure zones out, because then you have people that are living in a certain area that you really can't have a line go right past them unless you have individual PRVs to go to those individual houses or something, or reduce their pressure if you have some future project that would deliver a line through there, like a high surface line or something. Tank overflow primarily sets the pressure zones. You want to try and keep a range of somewhere between 150 foot of head, roughly 50 meters, and 80 foot of head, or 25 meters. static CAD. That's the rough approximate range that you would want to keep your pressure zones within. And if you have too broad of a range of differences in head elevations, meaning a very broad pressure zone, then you're going to deal with lots of high pressures in some areas and low pressures in another area, and it's going to be very tough to maintain because you're going to have different problems depending on where you are. And there's perhaps you might have to use higher pressure, more durable fittings or something in some high pressure areas, but all within the same pressure zone. If you have too narrow of a pressure zone, perhaps you're going to have more elements to manage than you need. You might end up with more pumps than you need necessarily to manage, more valves, more PRVs, more things you have to maintain or that require energy or capital cost. So too small of a pressure zone can have its own struggles. So in plan view, you might see something like that looks like this, or mapping out pressure zones. As soon as you go through a pump, that is a new pressure zone, and as soon as you go through a PRV, that is automatically a new pressure zone. And then of course the maximum water surface on an elevated storage tank, that's the top end of a pressure zone as well. And I'm going to show you some tools on how to, with Pressure Zone Manager in just a moment, to where it will automatically file things into different pressure zones for you. So Pressure Zone Manager is actually looking at pumps, turbines if you're into that and using those, check valves or other control valves as boundaries to say, yep, this is all one pressure zone. So Pressure Zone Manager will help you find where you potentially have some elements in. Maybe you filed it under one pressure zone, but it was inaccurately filed or something. So graphically, you're going to be able to see where pressure zones exist and where the breakout is. I've got some screenshots to show you here. So an example here, there are valves. Wherever you see color transition, there's either a valve or there's some type of pump station. I'm trying to circle them for you here. Here's another pressure zone. Here's another pressure zone. So what Pressure Zone Manager does for you is it will color code based on those boundary elements. So if you want to be able to automatically do this and identify them and display the pressure zones, you can use Pressure Zone Manager to do that for you. And then you can also look at the characteristics. This is probably of importance, is do a flow balance and have, for all of the pressure zones that are there, you would know how much flow went through one of these pressure zones. Now to set this up, you would go to the Pressure Zone Manager and select and tell the model which elements you want to be considered as pressure zone elements, the boundary conditions. So you'd specify those. The defaults are usually correct, but you can override them and change up the elements here as you need. Always use, don't use kind of thing. And then you can actually treat each pressure zone as having a bathtub of information, if you will. That a particular pressure zone has a certain number of nodes, a certain number of isolation elements, pipes, length of pipes, fluid volume. So maybe you're looking at a pressure zone needs to be shut off. So how many pipes are going to be in there? What's the fluid volume if you need to chlorinate that area because there was a leak or something, to calculate that. And you can view individual pressure zone results, fluid volume. You can create a selection set for these pressure zones. And here's another graphical view of using pressure zones, that whenever it flows through a pump, it's a change in color. When it throws through a control valve, like for example, here's a pressure reducing valve, that's creating a new pressure zone out here. We went through a whole bunch of pumps, so that became a new pressure zone. So it's just a very quick way to graphically see where everything is and make sure that you have things in the right zones if you are using zones as a feature of one of your elements. You can zoom into pressure zones because it's its own element now. You can right-click and zoom to and go straight to that pressure zone and create a selection set. You can look at the flow and the pressure into each pressure zone, minimum pressures, things like that. Some uses would be to determine if anyone in the pressure zone will have excessively low or high pressure, because you'll see over here on the right-hand side maximum pressure and minimum pressure. It's a very quick way to see what that range is on each of your pressure zones, because remember earlier I was saying there's kind of like a sweet spot range that works well, but then outside of that range it's tough to manage, or it's high variability for users, or it's a whole lot of equipment. So one I might be very interested in is this 9 psi. That could be a pump station suction that's causing that. That's a big range. These two look a little low. I would be a little concerned about the low pressure here. Here's another one I'd be concerned about. This is a big range, 154 to 13 psi. That's a pretty big range. So I would want to look into that pressure zone a little bit more and see if that's a reasonable range that everyone's going to be experiencing, or if it's just some pump suction somewhere. Now, what's the difference between zone and pressure zone? A zone, you can assign a junction or a pump or a tank to a zone. It's a property that you assign. It's a drop-down. You create the zones and you assign the zones. Commercial zone, residential zone, R1, R2, R3. You assign those to your nodes. You can do it graphically by selecting a whole bunch of them and apply it, or you can do it manually one by one by one. Pressure zones, on the other hand, is something that WaterCAD and WaterGEMS calculates for you based on the elements or constraints in those drop-down menus that I showed you earlier, where you pick the type of valve that is going to define the pressure zone. And the nice feature about this is pressure zones actually help you assign zones. So because your zones are probably going to be broken up by pressure zones in the first place, then maybe there's subsets within that. Okay. Now kind of moving on to the next topic here, master planning. If you're ever involved with the master planning, somebody is coming up with the estimated growth. And that estimated growth of where it's going to be, what magnitude it's going to grow into, and what phase or rate it's going to grow into, that is very useful information for you as a modeler to then incorporate into your design phases, or into modeling a 2020 versus a 2030 versus a 2040 model, and turning on certain pipes and increasing the demands with demand alternatives. So that's kind of how you would go through the thought process of using scenarios and alternatives to model different time periods out into the future. That is then going to help you begin to understand what infrastructure you'll need. Will you need an additional pipeline connection? I've got a few slides to kind of walk you through those examples. But by modeling out phases of development for master planning, you can kind of know what infrastructure, what capital improvement projects you're going to need, perhaps when. For master planning, generally you're making some higher level decisions. You're not trying to decide, should this pipe in this neighborhood be connected here, or should it be a 6 or an 8 inch? Generally, you're deciding, should there be a transmission line here? Should there be 2 transmission lines? Should they be, double barrel? Should it be one large? Should there be another pump station? You're making fairly large decisions at a master planning level. So the use of a skeletonized model can actually help you move more quickly, because you're only dealing with a few nodes or a few pipes, maybe if it's a super skeletonized model. You can also get away with using constant head nodes as pumps instead of actually putting in pump curves. The constant head nodes means it's going to be delivering a certain amount of head regardless of the flow. And you can even run extended period simulations at that point. And maybe master planning, you're trying to make sure that lake water levels, as they change throughout the season, that in this master plan, the pump station head is going to be enough to get it where it needs to go because of the net positive suction head coming from the reservoir or something. So you can make these pretty grand designs at the master planning level, but the more skeletonized model that you're dealing with, the easier it is to do that because you have less things to change. You can start to consider water quality implications with a master plan. However, you're going to not have as many loops and as many connections with a skeletonized model, so that's going to be a little bit of a tough one to accomplish. Pipe sizing. We're going to be working on a design when we start up tomorrow. We'll be working on the design of a piping network. And this is a good slide to refer back to on how you might go about using WaterCAD and WaterGEMS to lay out different pipes, different pipe routes, and determine what those sizes should be. So WaterCAD and WaterGEMS, it's not a savant. It's not going to be able to figure out where all the pipes should be. you as a modeler need to tell it where potentially a pipe might need to go to give it potential paths, because it could say, oh, well, surely, WaterGEMS and WaterCAD since it could say, surely there should be a pipe here, so it goes to draw it, but oops, it just drew it right through a hospital, or it drew it right through a lake. It's not intelligent enough to know that there's spatial elements are out there. You, however, are and can provide WaterCAD and WaterGEMS with some proposed piping paths and give it an initial selection set of sizes. If you're going to consider any demand estimates in the future, or if there's going to be a system outage, you can throw those things at it, and then make a model run based on the sizes that you picked. Reformulate the design, make sure it's meeting all standards and guidelines for pressure and flow everywhere, and then start looking at costs and go through the iterative process of which solution is going to be more efficient and more cost effective than the other. Now, you can go about through this manually, which is what we're going to do tomorrow and as well as Thursday. We're going to go through this process of designing, changing sizes. We're going to use Darwin Designer in a manual state, but it can also be used in an automated state to automatically go through these loop cycles for you to come up with the best solutions. So tomorrow we're going to appreciate going through the manual process and understand how that works. But this is important for layup for tomorrow. So with pipeline design, consider the route, wherever you're potentially going to go, and then whatever future phasing is going to come into play. Like, is there going to be a future transmission main that you can connect to somewhere? Any future pipes? There's another thought approach to throw at you here. We have a water source over here on the left-hand side. Here's our water source. Water's going through a 16-inch to an 8-inch to a 10-inch. And you're building some connection over here, some subdivision, some new part of the system. And they need a particular hydraulic grade. So here's the hydraulic grade they need. And your job as a modeler is to tell the engineering department, what size diameter pipe should connect to that subdivision or that other part of the system. And you try an 8-inch using your physical alternative, and you try it, and the hydraulic grade drops off, the velocity is too high in the line, head loss is too high, and it drops off. You try a 10-inch with another physical alternative in another scenario 2, scenario 3, 12-inch, scenario 4, now it's working. So the fourth scenario, you tried a physical alternative and change that pipe diameter to 16. And keep in mind when you're doing projects like this, the 16-inch may come at a cost. But another potential solution to apply would be with active topology, to turn on another new pipeline that goes back and removes the bottleneck. Because quite honestly, sometimes bottlenecks can occur, and in this case, the 8 and the 10-inch are the bottleneck. So you would consider a cost feasibility study of whether or not that 10-inch line and that particular length, cost of construction or whatever, is going to give you a better pressure benefit versus a 16-inch that's shorter, that's going to cost more, but perhaps it's only going to give you a certain amount of pressure benefit. So again, we're going to look at that tomorrow morning when we start off, is different solutions have different pressure benefits, and how do you quantify that difference. With subdivisions, they build out relatively quickly. Some things to consider, generally small pipelines in subdivisions, fire flow demands generally control the design, so there's going to be some minimum diameter. Here's an example of some subdivision planning. You have subdivision out here. Let's break it into phase 1 and 2. Here's phase 1. Here's phase 2. So we have phase 1, and we only need a 6-inch line to model for phase 1. But let's say you run the model and you want to see what happens for phase 2. Well, phase 2, you're going to need a 16-inch line because it's just a lot more flow flowing into the subdivision. So now you need a 16-inch line. So if you were going to run another scenario and say map it out into the future, there's some 24-inch line coming in. So you can phase the design of the subdivision by using active topology and demand alternatives to turn up the demands in the subdivision for a different time. You could see whether or not you can last just on the 6-inch alone until phase 2 comes online and then connect to the 24-inch proposed line that's going to be out there in the future. Or do you really need to install a 16-inch line, which is going to cost X number of dollars more because phase 2 is just not going to have adequate pressure early on, and it's not going to last until you get to the 24-inch line. So you can make some engineering design decisions of when things need to be phased or turned on or connected or installed. So if you are trying to ever simulate a connection to an existing system, but you do not know all of the controls, you do not know all of the demands, all the pump curves, it is all a mystery to you what's going on in this system. Okay? If you're ever trying to do that, this applies to you. You have some proposed development, something that you're trying to design out here, and there's a decision point here that you have. How do you model the existing system without having the existing system? Well, the solution to that is to first do a hydrant flow test at that connection point. What this is going to yield for you is the performance and behavior of the existing system. With a hydrant flow test, generally what that means is you take a static pressure when there's no flow. You haven't opened up a hydrant downstream at all, and you get a pressure. So that's what this is. Q is 0, P is 80, pressure is 80. Then you open up a hydrant downstream, and you simulate demand. You're simulating this proposed development demanding water on the existing system. And so you then draw some water off. You would see an equivalent reduction in pressure. So here we've got a new flow and pressure. Then you open up another hydrant, or you open up that one hydrant more, and you have a new flow and pressure. Now, keep in mind you're measuring flow and you're measuring pressure. For this to work, you need to be measuring flow and pressure. A lot of times I'll see a hydrant flow test and just see one pressure and one flow. I'll explain a few reasons why you might need some more information than that. The static pressure you definitely need. Having this third point is going to help you create a curve. So let's play with some numbers and let's convert 80, 64, and 53 multiplied by 2.31, which is a nice handy conversion from pressure to head. And now we're going to graph that, Q versus head. This data point here is going to be the static head right here. This data point is going to be the original 400 Q and 64P, and this one is 550 Q, 53P. Looks like a pump curve, and you know what? That's what it is. So now what we can do is we can simulate with a reservoir and a pump the connection to the existing system. Remember, we don't know everything that's going on in the existing system. We're running a hydrant flow test. And again, this is a question that comes up a lot. And I'm going to now go into your mind and help you with your thought process here. If you do this, if you elect to do this, that means that you're saying that that hydrant flow test is representative of all conditions that this existing system will ever produce. And if you believe that's the case, if you are confident that the hydrant flow test is the worst case conditions that that existing system will ever produce, then you're okay proceeding. If not, then that's something that you'll need to consider, is that the existing system could have maybe a different operating condition at different times of the year. And the hydrant flow test was only taken at one particular operating condition that was not the worst case scenario with the lowest pressure. And then also another piece to this too that I've seen before and comes up often is the question of, okay, I got a hydrant flow test from 6 months ago. Can I use it? And the response there, or the thought process to go through there is, well, has the system changed? Has the existing system changed since that hydrant flow test happened? Was there any improvements? Were there any more connections? Did they change the operating conditions? Did they change the controls? What time of day was the hydrant flow test taken? Was it taken during the high flow period where high demand period where pressures would be low? or was it taken at low demand periods where pressures would artificially be high? Meaning the existing system demands are low, so pressure is high. That means hydrant flow test would be giving you really high values, whereas if the existing system was being stressed during high demand periods, the hydrant flow test would give you lower pressure. So when was the hydrant flow test taken? Because if it was taken 6 months ago, what were the operating conditions? Did things change? What time of day was it? And go through that thought process if you ever do this step. Now, the other alternative is if you're not comfortable with this, you can model back in the existing system to some boundary condition. Model back to the point where you get the tank water or tank elevation or some pump station. You can model part of the network of the existing system back to a boundary condition. But again, you need to know what those controls are, boundary conditions, whatever the maximum ranges are and minimum ranges are. Very important if you do this type of thing to go through that thought process of how to leverage hydrant flow tests to your advantage and keep them from giving you, say, a false response or a false answer here and lead you to kind of shaky conclusions. Okay, modeling wells really quickly. Yes, we can model wells. There is not a model well element in WaterCAD and WaterGEMS. However, the way we get around that is using a reservoir and a pump, or as a negative demand. I prefer the reservoir and the pump because then we can actually model the true performance of the well pump. Okay, rehab studies. Maybe you want to use WaterCAD and WaterGEMS to help you along the way of doing a rehab study and figuring out if you change the C factor by installing a different type of pipe material, a different liner or something. You could use that with the physical alternatives and just simply change the C value with a new scenario, run the two, and compare your pressure benefit. Maybe you're doing pipeline replacements and you want to see and compare the results from one scenario to the other for fire flow tests. And that's something very realistic that you would probably be doing is replacing lines and seeing how that improves your fire flow delivery. A lot of different things you can do with rehab. Slip lining, clean line, fold and form, pipe bursting. To do all of these different techniques, a lot of them are changing C factors. And C factor is a property of the physical alternative. So you would create a child alternative of physical, and then simply just change the C factor for those pipes that you're going to perform this rehabilitation study on. If that rehab study is going to change the inside diameter, I would also include that. And include the proper actual real-world inside diameter for the lines before and after. That way you're really comparing what is the true difference in carrying capacity and volume and flow rate and head loss that you're actually going to experience by performing this rehabilitation on the pipeline. So to do that, you'd set up two scenarios. One alternative would be looking at the physical alternative for diameter and C factor, and then you'd create a child of that and just simply change the diameter and change the C factor for those lines. And then compare those two scenarios and you can see really how well it's going to work for you. Back when I was using WaterCAD and WaterGEMS, very quickly here, I was using it for an application engineering side as an engineer, using the software, and a lot of times modeling the startup of new facilities or if something needed to be rehabbed. That was kind of the mode that I was in, that type of engineering industry that I was in at the time. And I was using WaterCAD and WaterGEMS to help answer the questions for me of how we turn pumps on, when we turn pumps on, when we take a tank offline to service it, to have it repaired, can the system function for several weeks while that tank is being repaired or a pump is being serviced. So you can start answering these phasology kind of things. Maybe you need to change the pump out. How big of an improvement is that going to be if you change out the pump? And again, you could simply do this by two scenarios and change out the pump definition curve. We already walked through how to do that. Zone boundary changes, maybe that's something that you're looking at doing. What are the impacts going to be? Use the zone manager to see if you change your zone boundary, is that going to change the minimum and maximum substantially? And preparing for shutdowns. Again, like I said, taking a tank offline, you're about to shut down a tank and you want to know, if you need to issue any temporary drought conditions for that water system. Or you can think of the model as a flight simulator, if you will, because pilots, you don't just toss them the keys to a 747 and say, all right, off you go, go fly, without some type of training. So in this case, the model can actually be treated as operator training, to sit a new operator down in a chair and show them exactly what happens if you don't turn the pump on at 3 o'clock before the evening demand hits, because all the tank water level goes away in all of the tanks or something. And that way you can show how to break things or not do certain things in the model and not have to actually have everyone experience that negative side effect out in the real world. So think of it as a simulator, if you will. And then ultimately where this is all heading, and now there's a SCADA Connect tool for that, and this is kind of where industry is heading. It's real-time control and getting real-time data being fed into the model, making real-time decisions, then computing results, and projecting what the new status needs to be for certain elements. So real-time control is where it's all heading. And again, that's SCADA Connect. System head curves. I'll talk to you a little bit more about system head curves. Haven't given them enough justice here yet. As tank water levels change, the system curve is going to change because simply the positive energy in the system has been reduced. So in this case, there's a low tank water level and a high tank water level. When you're sizing a pump and you have your pump curve, are you modeling it to satisfy the high water level, the low water level, or maybe you're just curious to see what happens if there's a fire and what the new system curve looks like and how much flow we'll be delivering, because whenever there's a fire or a break, a lot more water can go out of the system, pressure decreases, therefore the pump can deliver more. So these decisions in how you choose to model the real world can actually drive how much more or less the pump is delivering. In the case of force mains and sewer systems, you could use WaterCAD and WaterGEMS to size a force main system. No problem at all doing that. Water's water. You might have a system curve during dry weather where one force main is on, and this is the system curve that you get. Or versus wet weather, when multiple lift stations are on, you have a much more steep system curve, and maybe it's much harder to get water into the force main because the pumps have to work much harder to overcome that pressure that's in the line, in that header line. So again, pump selection matters based on the conditions that you're throwing at it. In this case, are you looking at the high water level or the low water level for the tank? And then where that intersection point is, remember, wherever that system is operating most is where that pump is going to be running most. So if the efficiency bell matches up more with the low water level, then that's great if that's where the tank is going to be operating most. If it doesn't match up well with the maximum water level on the tank, then maybe you might need to pick a slightly different pump or change out the impeller a little bit. That way you're optimizing the pump and being as efficient as possible. And that's how you would probably answer that design, is just changing out the pump curve a little bit because you have a different pump impeller, and see how well that works. Very quick note about variable speed pumps. Again, I wanted to bring this up and talking about pump curves. So these are various pump curves. 90%, or that's 100%. This is the 90%, and this is the 80% mark. So these are speeds at which the pump is operating. Now, if this were the actual system curve that pump is pumping into, what does that tell us about the use of a variable speed pump? The system curve is actually the green line. And what does that tell us? If we were then to go say, okay, we're going to use a variable speed drive, is that a good decision or a bad decision or an okay decision? Let's go through the thought process. The 100% flow intersects here. 100% speed on the pump intersects there on the system curve. Reducing the speed on the pump to 90% intersects here. reducing the speed to 80%. Can anyone see where this is going? If we reduce it to 80%, what happens? You're not going to achieve what's necessary, and not only that, it's not even going to go on. You won't get anything out of it because there is no intersection at 80%. So effectively what that tells us is you can run the pump with the variable speed drive from 83% to 100%. And to be honest, that's not really a range that's really worth a variable speed drive and all of the hardware and everything else to get it to happen. So you would see things like this if you were running a system curve against a pump at different speeds and be able to see if it's really doing anything for you. Could look at pump combinations, look at wire-to-water efficiency, see if you need to have 3 pumps or 2 pumps, and here's a couple graphs to show you why pump combinations really even matter. Pump 1 in green, pump 2 in red, or 2 pumps in red. So in this case, by turning on 1 pump, it gave you a particular minimum maximum design flow. 2 pumps, it doesn't exactly double the flow of the pump necessarily, but it does give you a marked increase in flow, and you are able to deliver more flow against that system curve. So in this case, having 2 pumps does work out okay. Now let's look at 2 more, another example of some pumps. The green right here, this is pump B, and pump A is here. So these are the 2 pump curves. So this is A, I'll write it on the screen, and this is B. There's A and B. Now, in this scenario where the system curve is fairly flat, this is the system curve line right here. It's pretty flat, so if pump B is running, it'll intersect here. If pump A is running, it will intersect there. And the blue line is the pump curve when both are running. So in all 3 cases, pump A, B, and B, we're getting additional flow by turning more pumps on. Okay, that's operating the way it should. Now if we have a steep system head curve, let's look again. We've got pump A right here and pump B. So we've got intersection here for pump B. Great, okay, we're delivering flow. And now orange intersects here, and we're able to deliver some additional flow. Okay, that's fine. However, when we try and turn 2 pumps on, you see this blue line? We turn 2 pumps on, all of a sudden we're not getting any more flow even with 2 pumps on. So that effectively means that pump A is dominating and suppressing pump B. So we may as well not even be running pump B. This is an example of a very inefficient pump that's going to be either tripped out automatically, or it's just going to be costing you a lot more money than it should to even be trying to run it. You can view multiple pump curves, a lot of things. You would do all of this by right-clicking on a pump and view pump curve, so pretty quick to do that. Consider reliability. You can do this with your WaterCAD WaterGEMS model to extend the functionality of your water systems model. You can look at if there's going to be pipe breaks, look at valving, and prevent any potential negative or accidental contamination in the system as well, or figure out how it got into the system and how to prevent it from circulating to the rest of the system. And then all in all, you try to determine how good the system is to handle whatever you can throw at it. We're going to get into criticality and a tool that's in WaterCAD and WaterGEMS, but I want to ask you first to look at this screen, and the red dots, black outline red dots, those are valves. And your objective is to deliver flow from left to right. So deliver flow from left to right here. And if you had a pipeline outage somewhere along the way, if that pipeline occurred, would you not be able, pipeline outage occurred, where would you not be able to deliver flow from left to right to get it to go this direction? Let's put a break at 16. And now we can see, okay, so if there's a break here, we have to shut off this section based on segmentation. Oh, we now are severing the water source and cannot deliver flow from left to right. So criticality, the tool criticality, is going to help us see this, not just in one case, but on the thousands of cases that this may occur, very quickly and graphically. Just like we saw for Pressure Zone Manager, it was color-coded. Criticality is a tool that you can use if you have the isolation valves to very quickly and graphically rise all of the troubling areas to the surface. And last but not least, you can use the model to troubleshoot and diagnose any problems that you have with the model. Try and find partially closed valves. If a pump isn't operating on its pump curve, how do you find it? Well, you can compare two different pump curves, and you'll be able to see that that's why a pump isn't operating well, is because the system curve is pressure's too high or something. Now, all of this is kind of boiling down to, why would we not just want to have WaterCAD and WaterGEMS, the software, whichever one you have, just design the whole system for you? Open it up, point it to the shapefile, and say, all right, now go design. Go tell me everything you need to know, WaterCAD and WaterGEMS, and I'll come back after I've played a round of golf or something, and why not let it do that? Well, there's been a lot of research. Part of it is how to define the pressure benefit across the whole system, and how do you accurately say, well, this hospital needs to get better pressure than this car wash facility, or you as a modeler would know one is more important than the other, but the hydraulic model isn't going to know one type of node needs a different type of pressure over another, and to be making that decision. And also, the model may come up with, hey, you need a 6.6-inch pipeline, but you can't just go buy a 6.6-inch pipeline. There's actually some decision where you have to pick either a 6-inch or an 8-inch. And it gets to be kind of hard to determine if one solution's better than the other, because it brings pressure from one area, increases pressure in one area versus decreasing pressure in another area, and vice versa. Which solution is better? So at the end of the day, you're still going to need to be the one in the driver's seat looking at the solutions and trying to determine which one's better based on cost, based on pressure, based on a combination of the two. However, WaterCAD and WaterGEMS will bring and present those solutions to you and weed out a lot of the millions of other not-so-good solutions to give you the top solutions. You still have to use your good engineering judgment to decide which one is the one you're going to use.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.